Lecture 13, Differential Equations. I'm recording this lecture after a long time, and this is about the last chapter. We'll begin with the last chapter in our course. I call it chapter 4, and this is a technique. It's called the technique of Laplace transforms. So what is this technique? That's what we want to see. So this technique is particularly useful when you are solving non-homogeneous equations with constant coefficients where the right hand side is discontinuous. This is a technique to solve IVP or IVPs, particularly constant coefficient linear non-homogeneous equations with discontinuous non-homogeneity, with discontinuous right hand side. And this will be therefore very much useful in circuit theory. Very useful in circuit theory. Because that's where you get such equations about the current flowing through an electric network. Anyway, so what is this technique? So I want to introduce the idea of Laplace transform, which is another linear transformation on the space of functions. So a Laplace transform is a linear transformation. This is the first, I'd like to emphasize on this first, is a linear transformation on the vector space of functions exactly what kind of functions I will not go into that detail, but we'll just say vector space of continuous functions. Maybe I'll add a continuous here. It's not really neat. Continuity is not the key thing. On 0 infinity. So let me define this formally. Definition: given a function f on 0 infinity to r, define a new function which is called the Laplace transform of f, denoted by L of f, LF, called the Laplace transform of f. So define a new function denoted by this called Laplace transform by setting LF at the point S is integral 0 infinity e to the minus st ft dt. So it's a very non-trivial way of defining a new function. And so few comments on this. So some remarks. First of all, I want to quickly revise the definition of improper integral. This is an improper integral. So this integral, that is the one on interval 0 to infinity, that is the integral on 0 to infinity, is defined by, so if you recall, so this is recall Calc 2 where you learn these things, that integral 0 to infinity of any function gt dt is defined to be, so this is the definition, you take limit as m tends to infinity and you take the integral from 0 to m. If this limit exists, then we say that the improper integral 0 to infinity gt exists. So if the limit on the right hand side exists, we say that the improper integral (0 to infinity gt dt) exists, and or is convergent, and its value is given by this limit, and its value is given by limit as m tends to infinity. So this is the first thing about recalling what an improper integral means. So that's my first point. Second point is, so what are we doing to find out L of f? L of f, even before that, I will always denote, because your function f and LF both are functions, so I will denote the variable when it is referring to function f by t. So the variable used when we are talking about f about function f is t, and we shall use, when you are talking about LF, we shall use the variable s. Use s to denote the variable of the function LF. So that's number 2. So first of all, I recalled the definition of improper integral. Then whenever we are talking about a function which we are integrating as a function of t, and then LF is another function which is defined at variable s, so we will denote by s the variable. We'll use letter s for the variable when we are talking about Laplace transform of a function, as opposed to when you are talking about just the function, we use the variable t. Now, third thing is, we will see what this function is doing. So if you draw a picture of f, say suppose f is like this, e to the st for a fixed s, and I'm taking s positive, so e to the minus st is a function like that. So we are multiplying f and e to the minus st. That means as you go out, the effect of whatever f is going to be squashed down by this number which is e to the minus ft, which is getting very small. So in the beginning maybe your ft will have certain shape like that, but at the end it has to die down. So this is a very complex thing. You can think of this as f is sent into a black box or a mixer. I will call it a mixer, and you input e to the minus st. This is your mixer ingredient. You pass this function, and what comes out is L of f. So it's a grinding thing which is mixing f, mixing in the sense that you are taking f times e to the st, and then you are integrating. Then you are finding the area under the curve. This will be LF of s for a fixed s. So you are finding the area under the curve for a fixed s. You will get this. As s increases, this decaying factor will also increase in its strength. So the important point is LF is a mechanism. LF is cooked up from F by a very complicated mechanism. The important thing about LF is LF, so the why is this important? So let me address that. Why is LF important? And the answer to this can be given much later in a more convincing fashion, but at the moment I will just state that L converts differential equations into algebraic equations, and this will be explained later. Differential equations into algebraic equations. So what do I mean by this? This I will tell you as we go along, and this is why to solve a given differential equation, rather than looking at the differential equation which f satisfies, you look at the Laplace transform of this function. Then it will satisfy an algebraic equation which will be easier to solve. And then once you solve that, you go back to finding the function f which you were interested in. So this is the idea of solving a differential equation, which I will comment on a bit later. So this property of L will be crucial in this method of solving IVPs, given IVPs. Good. So now the third remark that I want to state is that L is a linear transformation. So this is a lemma which is easy to prove. L of f plus g is LF plus LG, and L of lambda f is lambda LF. This is why I revised a bit of ideas of coming from vector spaces, because this gives you a better understanding of what this L is. This is very easy to see, because what is L of f plus g at s? This is integral 0 to infinity e to the minus s times t f plus g at t dt. And this is simply, you know how this is going to go. This is ft plus gt. And then if you split this into two sums, you get e to the minus st ft dt plus integral 0 to infinity e to the minus st gt dt, which is going to be LF at s plus LG at s. And similarly, you can verify the other thing. L of lambda f is lambda LF. So in fact, the differential operators were one class kind of linear transformations that you have studied. This is yet another linear transformation on the space of functions, which will be very crucial. So just like we learned how to differentiate functions and integrate functions, the integration means it's the inverse of differentiation. Just like that, before we see the applications to differential equations, we will have to learn the language of Laplace transforms, meaning how to find the Laplace transforms and how to read the inverse transforms. So just like in Calc 1 and 2, we learn about finding df given f, and this was the differentiation, and given g, finding f such that df is g. We call this integration. Similarly, we want to, so similar to this, just like in Calc 1 and 2, in Calc 1 and 2 we learned, did I say that? Yeah, we learned about finding f. Here we want to learn about, first, given f, finding LF, and more importantly, given G, finding an f such that LF is G. This is called the inverse transform, finding the inverse Laplace transform. Good. And so first we want to spend some time on this, and then we want to get some expertise in doing this. Then we will see how this operator, this linear transformation, changes differential equations into algebraic. And so to solve a differential equation, we will look at not the solution y, but its Laplace transform. It will satisfy an algebraic equation. And once you solve that, you read off the function f, whose Laplace transform is that solution of the algebraic equation. So that will be the approach to solving an initial value problem. Good. So first we want to spend time on, so first we want to build our dictionary, so to speak, of given f, what is LF, and how to read off f given LF. So we begin by creating a list of LFs for some standard f's. And then we will learn the techniques of finding the inverse transform. So let's begin with the first example. Let's take the function ft equal to 1. So our functions are only going to be on the positive axis. This will be, so this is like in terms of the electric circuits, you turn off the switch in an electric circuit at time t equal to 0. So previous to that the function is 0, and then it starts. So this is the picture of ft in general, and this function is just 0 till 0 and then 1 after 0, constant function. So what is LF of this? So which is L of 1. This function at s by definition is integral 0 to infinity e to the minus st 1 of t dt, which is simply 0 to infinity e to the minus st dt. 1 of t is just 1. So by definition, this is limit as m tends to infinity, integral 0 to m e to the minus st dt, which is limit as m tends to infinity, integral of e to the minus st is e to the minus st by minus s from 0 to m. And this gives you minus e to the minus mt. I'm putting t equal to m, so e minus sm. Maybe I'll do it like this. Minus sm by capital M, of course, by s minus e to the 0 is 1 by s. And so if you look at this limit, this will be just 1 over s, because this limit tends to 0. So we have our first important rule. Laplace transform of the function 1 at s is 1 over s. So now let's look at the function t. So example 2, let's take ft to be t. So then we want to find LF at S, and this is going to be again integral 0 to infinity. Let me write this, e to the minus st times t dt. So this is lim as m tends to infinity 0 to m e to the minus st dt times t dt. So you have to use integration by parts here. So this will be limit as m tends to infinity. I integrate first of all e to the minus st, so e to the minus st by minus s times the other function minus integral integrated thing, which is e to the minus st by minus s times the derivative of t, which is 1. So this is going to be limit m tends to infinity. So because of the negative sign, I evaluate this at 0 first. So I will get at t equal to 0, you will get 0. Minus at t equal to m, you get minus sm by s. Then I will get plus limit m tends to infinity. I will pull out 1 over s. And then I'll get integral of e to the minus st, which is e to the minus st by minus s between 0 to m. So this limit is going to be 0 minus 0 because e to the minus sm tends to 0 as m tends to infinity. The second one will give you, let me pull out 1 over s square, and I have a negative, so I start evaluating this at 0 first, which will give me 1 minus e to the minus sm. And of course there is a limit as m tends to infinity. So you will see that this will be, maybe I'll write it more clearly here. So this is going to give you just 1 over s square because this limit will tend to 0. So we have our second formula, Laplace transform of t. So I want to start making a table, f versus LF. So if f is 1, Laplace transform is 1 over s. If f is t, so remember the variable of these functions, when you are talking about f, the variable is t. When we are talking about LF, the variable is s. So Laplace transform of t is 1 over s square. Let's now take the third example. Let's take ft to be t square. So Laplace transform of f at s is 0 to infinity e to the minus st t square dt, which is lim as m tends to infinity 0 to m e to the minus st t square dt. Let's just evaluate e to the minus st t square separately. This will involve integration by parts twice. So I first integrate e to the minus st by minus s times t square minus integral integrated thing times the derivative of t square. So this is going to be minus t square by s e to the minus st. This will be plus 2 by s integral e to the minus st times t dt. So that has lowered the power of t by 1, and now we want to use integration by parts one more time. So you get integral of e to the minus st is e to the minus st by minus s times t minus integral integrated thing times the derivative of the other, which is 1. So this is minus t square by s e to the minus st minus 2 by s square e to the minus st. Minus minus is plus 2 by s square. And integral of e to the minus st is e to the minus st by minus s. Good. So what do we get? So you get t square by s e to the minus sign e to the minus st minus 2 by s square e to the minus st minus 2 by s cube e to the minus st. So if you evaluate this between 0 to m, this will be the value of this function at 0. Let me calculate this at, I'm evaluating between 0 to m, so I evaluate this at m first. So I get minus m square e to the minus mt by s minus 2 by s square e to the minus mt minus 2 by s cube e to the minus mt. All of this is going to tend to 0. Minus the value at t equal to 0 will give me 0. I have a t here, I have a t here. Minus 0 minus 2 by s cube. So when I take the limit, so LF will be the limit as m tends to infinity, integral 0 to m e to the minus st t square dt. This limit will be simply 2 by s cube, because all of these terms will tend to 0 and you are left with 2 by st. So we came up with, so now I update my table again. F versus LF. F is 1, LF is 1 over s. F is t, LF is 1 over s square. F is t square, it is 2 over s cube. Now you see why you got 2, because when you are differentiating t square, that is why you get 2t as a derivative. So if you had a t cube, you will get 3 times t square, and then you multiply and then you differentiate it again. That will give me 3 times derivative of 2. T square is 2t. So that's how you are going to get 3 times 2t. 3 times 2 divided by s to the 4. So what's going to happen if you keep on differentiating? You will arrive at the formula derivative of t to the n will be factorial n over s to the n plus 1. So that's the first important rule that you know. Ft is t to the n, then Laplace transform of f at t is factorial n over s to the n plus 1. Good. So let's see another example, another nice function, which is e to the at. So let's take ft to be e to the at, and let's find out LF at s. This is again 0 to infinity e to the minus st times ft, which is e to the at dt, which is integral 0 to m e to the minus s minus at. And then if you just look at what this limit is as m tends to infinity, 0 to m e to the minus s a t dt, which is going to be lim as m tends to infinity e to the minus sat, integral of that is e to the minus sat by the constant, which is minus s minus a, and that will be between 0 to m. So this will be limit as m tends to infinity. The value of this function at m is minus e to the minus s minus a m by s minus a, minus when t is 0, this gives you 1 over s minus a. And as before, this first limit tends to 0, and you will get the answer to be 1 over s minus a. So now I update our table again. You have seen that t to the n, the Laplace transform is factorial n over s to the n plus 1. And when the function is e to the at, Laplace transform is 1 over s minus a. Next, I want to add to these two other functions. Let's take sine at and cos at. And we'll see what the Laplace transform turns out to be. So another example. Let's take ft to be sine at. So LF at s is going to be limit. This is a limit as m tends to infinity, 0 to m e to the minus st times ft, which is sine at dt. Now this integral is trigonometric times exponential, and so it needs time to evaluate, because we will have to use integration by parts twice to do this. So let's do this carefully. Okay. So let's call this integral I, integral e to the minus st sine at. We'll worry about the limits later. So when you integrate, you get e to the minus st, so integration by parts, over minus s times sine at, minus integral integrated thing times the derivative of the other, which is derivative of sine at is cos at times a. So this is going to be minus e to the minus st sine at by s, minus minus plus, and then you have integral e to the minus minus st cos at dt. So I integrate again by parts. So what do we get? 1 over s, integral of e to the minus st is e to the minus st by minus s times cos at, minus integral e to the minus st by minus s, and derivative of cos. I forgot one thing, I forgot this a. So derivative of cos at will be minus sine at times a. So this becomes e to the minus st sine at by s minus a by s square. This is minus also. E to the minus st cos at. And then I'm going to get minus minus minus, 3 minuses, so minus sign. A by s and another a by s will give me a square by a square. Integral e to the minus st sine at. But this is exactly your I. So you get I equal to minus e to the minus st sine at by s minus a by a square e to the minus st cos at minus a square by a square times I. So what will that give? So you move this term to the left, so you get 1 plus a square by a square. You recall your how you do integration by parts integrals of trigonometric times exponential. You start by calling the given integral as I, and you apply integration by parts twice. This is what we have done. So this is going to be minus e to the minus st sine at by s minus a by s square e to the minus st cos at. So if you simplify this times I, of course, so you will get here s square plus a square by s square I equal to that. So I will be s square over s square plus a square e to the minus st sine at by s minus a by s square e to the minus st cos at. Good. And now we are going to write down L of f at s, which is lim m tends to infinity. We have to evaluate this between 0 and m. So what will be the value at m? It is minus e to the minus sm sine am by s minus a by s square e to the minus sm cos am. This stuff minus the value at 0, which will be the value at 0 will be, first term will be 0 because sine of 0 is 0, minus sine, and minus sine, second term will be at t equal to 0, e to the minus st is 1 and cos of at is also 1, so it's minus a by s square. So this is going to be s over s square plus a square. All these terms with exponential e to the minus sm will tend to 0, and you will be left with a by s square. I should have had an s square here. Yes, that's what we have. So this gives you a by s square plus a square. So now I update my table one more time, and I'll write to you the first important table that we have achieved after doing this table of Laplace transforms. So if f is 1, Laplace transform is 1 over s. For a function t to the n, it's factorial n over s to the n plus 1. For e to the at, it is 1 over s minus a. For sine at, it is a over s square plus a square. And now I give you this as an exercise. For cos at, it will turn out to be s over s square plus a square. So that's our basic table for Laplace transforms. Now we are going to use, so as I told you, that we need to get the expertise of figuring out Laplace transform, and given a function f and given a g, how to figure out f whose Laplace transform is g, that is the inverse transform of g. So let us try maybe a couple of problems first. So some examples. After this table we should do this few examples. So I'm more interested in finding the inverse transforms. So let's try to do the problem on finding the inverse transforms. So find f given that LF at s is equal to 5 over s plus 3. So you have to recall, you have to have your table in front of you. So e to the at gives you 1 over s minus a. So you can see, so f, you can write this in the following way. This is the inverse transform, which is L inverse 5 over s plus 3. Because L is linear, its inverse is linear, so you can pull out 5 and you will get 1 over s plus 3. So since L inverse is linear, so L is a linear transformation, so its inverse denotes the inverse of the linear transformation. And now this is corresponding to a equal to 2. By the formula you see this is e to the minus 2t. So f is e to the 5 times e to the minus 2t. Laplace transform of f will be 5 over s plus 3. Good. Let's do another example. So rather than finding the Laplace transforms, finding the inverse transform is more important. And let's do this one. Find f given that LF of s is 3 over s square plus 16. Now you see that this formula is going to be, you compare it with the table, so you have to apply the formula for sine 80. Here a will be, well, sine of 80 Laplace transform is a over a square plus a square. Here you have in the denominator a square plus 16, so your a should be 4. You have 3 on the top, so you write it like this. This is L inverse by 3 over a square plus 4 square. So I want to write this as 4 over a square plus 4 square, and you multiply it by 3 by 4. Because now I can write the inverse transform. 3 by 4 is a constant that comes out. Then you can write the inverse transform of 4 over a square plus 4 square. That's sine 4t. Good. Now we can add a trick of partial fractions to this. So let's do that problem. Find f given that LF of s is 4 over s plus 1 times s plus 2. So use partial fractions. So use to write this right hand side as a sum of terms of the form constant over s plus 1 and another constant plus s over divided by s plus 2. So let us write 4 over s plus 1 times s plus 2. This has a over s plus 1 plus b over s plus 2. So therefore, what does that give you? So therefore 4 must be identically equal to a times s plus 2 plus b times s plus 1. You have done this before in finding partial fractions in Calc 2. So that gives you 0, which is a coefficient of s to the 1, and that's going to be a plus b, and 4, which is the coefficient of s to the 0, is 1 times a plus, what did I do? This is 2. So it's 2 times a plus 1 times b. So you want to solve this system. B is minus a from the first equation. If I put that in here, I get 2a minus a equal to 4. So my a will be 4 and b will be minus 4. Good. So that gives me the partial fractions of 4 over s plus 1 times s plus 2 as 4 over s plus 1 minus 4 over s plus 2. Therefore, f, which is the inverse transform of 4 by s plus 1 times s plus 2, is L inverse of 4 by s plus 1 minus L inverse of 4 by s plus 2, which is 4 comes out. It's L inverse of 1 over s plus 1 minus 4 comes out L inverse of 1 over s plus 2. And you know that 1 over s minus a is the Laplace transform of e to the at. So here a is minus 1 and the second one a is minus 2. So this is e to the minus t minus 4 e to the minus 2t. So this is how you find the inverse transforms by using the table. But now we need to add few more rules. So now we study a few additional rules which will help us in calculating the Laplace transform, and as well as it will help us finding the inverse transforms. So I want to add 2 rules, and that will be the end of this lecture. First of all, Laplace transform of the derivative of f prime. So let's come to this formula. So what is the Laplace transform of the derivative of a function? So if I look at f dash s, this is going to be integral 0 to infinity e to the minus st f prime t dt, which is going to be limit as m tends to infinity integral 0 to m e to the minus st f prime t dt. Now I use integration by parts. So I integrate f prime first. So what will I get? I get ft times e to the minus st minus, this is between 0 to m, integral 0 to m, integrated thing is ft times the derivative of the other, which is e to the minus st times minus s dt. So this is going to give you m tends to infinity. Now I will get fm times e to the minus sm minus f0 e to the 0 is 1, and what you have here is minus and minus gives you plus s times integral 0 to m ft e to the minus st dt. But if you look at this, what will happen? This limit is 0. Then you are left with minus f0 plus s times limit m tends to infinity 0 to m f e to the minus st ft dt, which is exactly the Laplace transform. So this is minus f0 plus Laplace transform of f. So what happens s times? So what happens is, let me write this formula as LF prime at point S is S times LF at S minus F0. In this sense, now you see what happens. If I pass, think of this like engineers do, the linear transformation as a kind of black box. You pass F into it, what comes out is LF. So if I pass F prime, what comes out is S times LF. In other words, differentiation on the left side gets converted into a multiplication on the right side. So this formula is the indication of why differential equations are going to be converted into algebraic equations. So note that L, roughly speaking, L converts differentiation into multiplication in some sense. This is not literal, not to be taken literally. What it means is, if I take f prime and pass it through this box, what goes out is s times LF and a constant minus a constant. In that sense, it converts into multiplication. So this is a very useful formula, and we are going to use this later on to solve differential equations. But let me do one more, and we'll see that Laplace transform of integrals boils down to dividing by s. So I do one more formula, and that is, let's calculate this. So let's call gt to be integral of from 0 to t f tau d tau, and let's find out L of g at t, which is going to be integral 0 to infinity e to the minus st g t dt. And what is this? This is lim m tends to infinity integral 0 to m e to the minus st gt dt. And now what I would do is I integrate g first. Notice that integral of I integrate e to the minus st first because I want to differentiate g. Notice that g prime t is ft. So if I integrate e to the minus st, I get e to the minus st by minus s times gt minus integrated thing times the derivative of g. and that's going to give me lim m tends to minus infinity e to the minus sm by minus s gt minus at t equal to 0, what do we get? At t equal to 0 you get e to the 0, which is 1. So you get 1 by minus s g of 0. And then I will get plus lim as m tends to infinity, minus minus comes out 1 over s integral 0 to m e to the minus st g prime is f. So now you see that this is going to be 0, the first limit is 0, g of 0 is 0, notice that g is just the integral from 0 to t, so note that g of 0 is 0, so this becomes 1 over s Laplace transform of f at s. So in other words, Laplace transform of the integral 0 to t f tau d tau at s is equal to 1 over s lf. So integration gets converted into division by s. That's the way you would like to remember this. Integration gets converted to division by s. So differentiation gets converted into multiplication by s and integration gets converted into division by s. Let me list all these properties and then I will tell you how to use the formula for finding the Laplace transform of the integral to figure out inverse transforms of the function. The formula for the derivative will not be useful for reading of the inverse transforms. So we have seen so far, so the summary is the following. So there are two things to keep in mind: the table f versus lf. F is 1, Laplace transform is 1 over s, t to the n is factorial n over n, s to the n plus 1, e to the at is 1 over s minus a, sin at is a over s square plus a square, cos at is s over s square plus a square. This you are going to verify. And the rules, so I will call these tables and rules. Rules, the very first is Laplace transform is a linear transformation. L of f plus g is lf plus lg. L of lambda f is lambda lf. And then the rule for differentiation, L of f prime is s times lf minus f of 0. And L of integral, this is, I'm writing it in a crude way rather than giving you the variables on the left side. So these are the two rules which we saw today. So let's do one or two more problems and that will end this lecture. So one more problem. So we shall see how to use the formula L of integral of f is 1 over s lf to find the inverse transforms. So let's do an example. Find f given, let's do the following. Given that LF of s is 1 over s times s square plus 4. See, doing partial fractions of this will be complicated. Note that without this s, you could find the inverse transform. Note that we can find L inverse of 1 over s plus 4. And so this formula for the integration tells you that the function whose Laplace transform is 1 over s times s square plus 4 will be the integral of the function whose Laplace transform is 1 over s square plus 4. So that is, if f is L inverse of 1 over s square plus 4, then integral 0 to tf is L inverse of 1 over s times s square plus 4. So this is how you will use this formula. So now so first we find L inverse of 1 over s square plus 4. This you know how to do because this is s square plus a square. A square is 4, so a is 2. So you would like to have 2 on the top, so you divide by 2. Then you can recognize this as L inverse half times L inverse of 2 by a square plus 2 square, which is the inverse transform is sine 80. A is 2, so it's sine 2t. And therefore, the inverse transform of 1 over s times s square plus 4 will be the integral 0 to t of half sine 2t dt, which is half integral of sine 2t is cos 2t by minus 2 from 0 to t. And so the value of this I will write as 1 over 4. Value at cos t is minus cos 2t, and value at 0 is 1, minus of minus 1. So the answer will be 1 minus cos 2t by 4. Similarly, if you have a factor of 1 over s square, then you will have to integrate twice. So let me do maybe one more problem, and that should be the end of this. Let's do something like, so another example. Let's do 1 over s square times, I can make it more complicated, but no, I can make it like this. Hold on, we have done one problem before. Let me pick that one and then I add a s square in the denominator. Yeah, let's take this problem. 4 over s plus 1, s plus 2. We did that before, right? So 4 over s plus 1, s plus 2. So let's find out so how should I put it? Let me erase this and say find f where LFS is 1 over 4 over s square times s plus 1, s plus 2. So we know we have already done this. We know that L inverse of 4 over s plus 1, s plus 2 turned out to be, what was that? Four e to the minus t minus 4 e to the minus 2t. Right, let me double check that. Yeah. So therefore, now you have s square here. So I'll have to do this in 2 steps. So L inverse of 4 over s times s plus 1 times s plus 2 will be simply the integral of this between 0 to t. 4 e to the minus t minus 4 e to the minus 2t dt. That's what the formula for the Laplace transform of the integral says. And so when you do this, you get 4 e to the minus t minus sine, and then this will be plus 4e to the minus 2t by minus 2 will give you that. That's between 0 to t. So this is going to be minus 4e to the minus t plus 2e to the minus 2t minus the value at 0 will be minus 4, and this will give you plus 2. So this is going to be minus 4e to the minus t plus 2e to the minus 2t, and this will be plus 2. So therefore L inverse of 4 over s square s plus 1 times s plus 2 will be the integral of this expression from 0 to t. So it's minus 4e to the minus t plus 2e to the minus 2t plus 2 dt. So this is how you will use the formula for the integral of Laplace transform of the integral to figure out the inverse transforms. So this is going to be minus 4 e to the minus t by minus 1 plus 2 e to the minus 2t by minus 2 plus 2t between 0 to t, and that will give you, let me write this as 4 e to the minus t minus e to the minus 2t plus 2t between 0 to t. So this is going to be 4 e to the minus t minus e to the minus 2t plus 2t minus the value at 0 will be 4 minus 1 plus 0. So this will give me 4 e to the minus t minus 2 e to the minus 2t plus 2t and the sum will be, this is going to be minus 3. I think I'll stop here. So the next thing that we will do are two more important formula. So we have two more important formulae to study, which will help us read off the inverse transforms, and also we'll be able to do the problems on differential equations. Now let me see, maybe I have enough time to do one problem on showing you, demonstrating how to do the differential equations. Let me do that, but before that let me finish what I was writing. So we have two more important formulae. We call them shift formula 1 and this will be for the next lecture. But now in the next 10 minutes I will show you how to solve an initial value problem using Laplace transform. So now we shall see how to solve an IVP using Laplace transforms. I'll do one example and then we will continue with this next time. So consider the IVP. So here is another example. Consider the IVP y double prime plus 3y prime plus 2y equal to 0 with the initial condition y at 0 equal to 1, y prime 0 equal to 0. Find yt. So we start by taking Laplace transform of both sides. So take L of both sides. So what do we get? We get L of y double prime plus 3y prime plus 2y. Y is a function, keep that in mind. L of 0. L of 0 is 0. So now I will recall a few things. Recall that L of 0 is 0. L of y prime, L of derivative of the function is s times Ly minus y of 0. And so now I will derive a formula for L of y double prime. L of y double prime will be L of y prime. y prime's prime. So it is going to be s times L of y prime minus y prime 0. So it's going to be s times, now I write L of y prime as s times Ly minus y0. So this gives you a formula for the Laplace transform of the second derivative. It will be s square Ly minus sy0 minus y prime 0. So therefore, what do we get? We will get s square Ly minus sy0 minus y prime 0. That's your Ly double prime. So I have to use the fact that this is a linear transformation. So this gives you L of y double prime plus 3Ly prime plus 2Ly equal to 0. So I'm writing, maybe I'll do it more properly. My trying to get the, yeah, let's try this. Yeah, so L of y double prime, what was our problem? Plus, it was 3y prime plus 2y equal to 0. Therefore, L of y double prime plus 3Ly prime plus 2Ly equal to 0. Since L is a linear transformation, and now I'm going to use that formula. So this gives you L square Ly, s square Ly minus sy0 minus y prime 0. That's your Ly double prime plus 3 times Ly prime is s Ly minus y0 plus 2Ly, that should be 0. So this will give you an equation for Ly, and which will be algebraic. So I collect Ly together, I get s square plus 3s plus 2Ly minus, what do we get? Minus sy0 minus y prime 0, and then this product will give you minus 3y0 equal to 0. Now you know your initial conditions. Y0 is given to be 1, y prime 0 is 0. So since y0 is 1, y prime 0 is 0, we get s square plus 3s plus 2 Ly equal to, or minus, let's do it slowly, minus s, y prime 0 is 0, minus 3 equal to 0. So that gives you s square plus 3s plus 2 Ly equal to s plus 3. And that means Ly, which is a function of s, is s plus 3 over s square plus 3s plus 2. So you see, y satisfies a differential equation tells you that Ly is an algebraic function. We have already solved the equation on the right hand side. We know what Ly is. So now you see that why taking the inverse transform, or the ability or the skills to read off the inverse transforms, is very important, because now you have to read off y from the knowledge of Ly. And now you do the partial fractioning, and we have learned enough to figure out this inverse transform. We will use partial fractioning, and so we will learn additional techniques of figuring out the inverse transforms in the next class. Let's finish this by writing this as in the partial fraction form. So you should get s plus 3 to be identically equal to a times s plus 1 plus b times s plus 2. That gives you 1 equal to a plus b and 3 equal to a plus 2b. So if I take the difference, I get minus 2 is equal to minus b. So b is 2, therefore a is minus 1, isn't it? Yeah. So therefore y will be inverse transform of a is minus 1, so it's minus 1 over s plus 2 plus 2 over s plus 1. So this is going to be minus L inverse, because L is a linear transformation, so is L inverse. And you get this. And you know from the table this is e to the minus 2t, and the other thing will be e to the minus t. So the answer to this is 2 e to the minus t minus 2 e to the minus 2t. Sorry, there is no minus 2. So that's how you solve a differential equation using Laplace transforms. So more later. So we will need more skills on finding the inverse transforms, but you see the mechanism. So what I started out with by saying that Laplace transform is a device for converting differential equations into algebraic equations, you can see that in this problem how this goes. You start by taking Laplace transform of the given initial value problem, you get an algebraic expression for Ls, and then it's a question of finding the function whose Laplace transform you know, and that's how you figure out the solution. So the skills of reading of the inverse transform are very important in this game. Just like in the case of calculus, reading of the inverse of a differential or derivative operator, which is integration, was a very important skill. Just like that, the analogy of that with derivatives is reading of the inverse transforms. So we are going to learn 2 additional tools for finding the inverse transforms in the next lecture. So I shall